everybody. Maybe we can start. There are already more than 20 people, although, there are people joining. Maybe we can start introducing our speaker of today's Athena webinar. Our speaker today is Fabio Acero, who obtained his PhD in astronomy in 2008, studying supernova remnants in the X-ray band. He's now a researcher at the CEA in Saclay. He's also members of Fermilab, CTA, and the Athena collaborations, and he's also an internationally recognized expert in high-energy data analysis of X-ray and gamma ray, especially on supernova remnants and diffuse stuff, and all the physics behind all this particle acceleration in supernova remnants. So I'm very happy to have him here in this Athena webinar and to know about supernova remnants and the current status of his research. Go ahead.
Okay, thank you a lot. Nana, can you hear me okay? Yeah.
Yes, perfectly.
Okay, and thanks a lot for the invitation. It's a pleasure to be here and to bring some nice pictures of supernova remnants and the amazing science that we will be able to do, that we can do now with X-rays, and that we will be able to do also in the near future with high-resolution spectroscopy. So this will be focused on supernova remnants, mostly about what the remnant can tell us about the supernova. So we'll not be discussing much about particle acceleration, which is another aspect that is studied in supernova remnant. Then what the high-resolution spectroscopy will be able to bring us to study these aspects. And also I will spend some time at the end discussing the challenges that we will face and that we are facing right now already to study those kinds of objects. So I would like to highlight also that this presentation will feature some of the works from our PhD student at Saclay, Adrien Picnot, Leila Godino, and Julia Lascar, and the collaborators that have helped produce the science that will be shown here, Anne de Courchel, Salvatore Orlando, and Jean Ballet. The supernova, so the stellar explosion in the galactic ecosystem, play multiple roles. And so you have, and there are different science that can be studied in this ecosystem here. So the supernova, of course, one of the questions that will be discussed here is how do they explode? What are the mechanisms for the explosions? And what we can study supernova, the light curve when they are far away, but we cannot study really the spatial extension and the distribution when they are extragalactic and very far away. But what we can do is study the supernova remnant centuries after the explosion, and there are fingerprints of the explosion mechanism that are left in the remnant. And of course, in the supernova remnant, we can study the nucleosynthesis, as I said, cosmic ray acceleration, supernova. Of course, the supernova play a very important role in the galaxy by injecting kinetic energy, heavy elements in the chemistry, etc., and by shaping the galaxy and the interstellar medium. And also something, those are nested like Russian dolls, where you have the supernova remnant, then you have the pulsar wind nebulae when they are core collapse, and inside you have the neutron star. So you have all those different physics that you can study. And in some cases, like in the case shown here in MSH 1552, you have also this interaction between the wind of the pulsar and the remnant that can be very interesting to study. And so mostly in my work, what I've been doing is studying those different objects via high energy observation, mostly X-rays and gamma ray with ground and space telescopes. So just a brief introduction on the supernova. One thing that I like personally that is with those objects is that they have a link with the history, at least those historical supernova. They are one of the rare objects where you can really look at historical records, for example, Chinese record or European record, and try to have the age of those objects. It is notably hard in astronomy to have an idea of the age of anything in astronomy, but this is one of the rare cases where we can know the age of the supernova down to 1 day precision. And so this is the case with all those historical remnants. So here you see, for example, some Chinese record mentioning the appearance of a new star, SN 1054, that is now known as a crab. And in the last millennia, we had about 5, only that we know 5 supernova in 1 millennia. 87A was in the LMC. And so the last one was 1604, so no galactic visible, at least from Earth, supernova in the last 400 years, when we know that the expected rate is more or less 2 per century. So either this is small numbers, Poisson distribution, or some of them can be also far away and we don't see them because of the extinction. And a little bit more than a year ago at the EAS in Valencia, we celebrated the 450 years anniversary of one of the recent one, Tycho supernova. And there was a special session about this at the EAS. And so Tycho supernova at that moment was brighter than Jupiter. It was seen in November 1572. And Tycho Brahe reported a lot about his observation. He was not the only one. It was witnessed, of course, by anyone. It was brighter than Jupiter in the northern hemisphere, but a lot of scientists at the time wrote reports, but we mostly remember the ones from Tycho. And so this was, of course, at the time, nothing was known about supernova. This was called nova stella, so about the new star that appeared in the sky. And one interesting thing is that so Brahe died in 1601, and his work on 1572 was only published after his death by Kepler. So Kepler really was the one who finished and published the work. And by luck, this is a once in a millennia luck that he was able to witness 1604, which we now call Kepler supernova. And so in the end, it is Kepler that published the two books on the supernova, on the galactic supernova. So by today's standards, we will say that two publications on supernova is a rather low H index, but you will agree that this is an outstanding chance to be able to publish two works on galactic supernova that has been witnessed at the time. So what is a supernova remnant? So the structure here is a schematic view. So the idea is that you have that kinetic energy that is injected via the explosion inside of the star that will disrupt and make this giant explosion. And all the ejecta are ejected, the surface and the stellar remnants. And so you have that forward shock that is propagating at a very high shock speed. We measure about 5,000 kilometers per second centuries after, but at the moment of the explosion, it's much higher than that, 10, 15, 20 kilometers per second. And this will create a shock wave which will shock the interstellar medium, the circumstellar medium, up to X-ray temperature, so 10 to the 7 Kelvin. And so these gas will be visible mostly, will peak mostly in the X-ray band. And then there is a reverse shock that will start to propagate inside of the star. And this is called the reverse shock, and which will shock the ejectas that are shown here in yellows. And usually they have not that perfect spherical feature because you have those Rayleigh-Taylor instability that are creating those fingers. And then in the images, what we see are patches of hot ejecta. At the same moment also, you have that very high shock speed wave here that will accelerate particles that will enter and be shocked back and forth at the shock wave, and that will bring cosmic rays, highly energetic particles, to the pool of galactic cosmic rays. And supernova remnants are thought to be one of the key sources of cosmic rays in our galaxies. So what can we learn by studying those objects? So we can learn many things, and so we can learn about how, where do galactic cosmic ray come from? What is the acceleration that occurs at the shock to accelerate particles? We can study also the collisionless shock physics. So for example, how do we hit a gas in such a case? How does the equilibrium between ionization, temperature works when you shock a gas? And then mostly today we'll be talking about what we can learn from the ejecta. So we can learn, of course, many things as we will see about the supernova explosion mechanism, the supernova type, because of course, when we look at the supernova remnant, we don't know at the beginning whether it comes from a core collapse supernova or thermonuclear supernova. Then we can learn about the progenitor, etc. And so the idea is that by looking at supernova remnants across the band, the spectrum from radio to X-rays to gamma rays, we can try as a puzzle to try to answer parts of those different questions here. So mostly I will be talking about shocked ejecta, but I wanted to show one thing about collisionless shock physics. So the idea is that you have that shock propagating here as a function of radius that is expanding, and at the shock you will hit the gas, and so the shock hitting is proportional to the square of the velocity shock and to the mass of the particle that is being heated. And so what you have is that ions will be heated to a higher temperature than electrons. And so typically for a shock speed of 5,000 kilometers per second, we expect that the ions, a proton, for example, will be heated to about 50 keV. And the electrons, if you look at the mass ratio of proton and electron, the temperature of the electron at the shock should be 30 eV. And that is not what we measure. In what we measure with X-ray, with Chandra XMM Suzaku, has been around 0.5, 1 keV or something. And so there's been a debate in the community about what is the exact mechanism that is taking place at the shock, and if there is some prompt heating mechanism that will take into account Alphen waves, etc., and to understand the physics here. And also, if you look at the temperature of oxygen, this will be higher than a proton, etc. And so the issue so far is that with CCD cameras, we don't have the resolution to measure the temperature of the ion line broadening of the protons, and we are sensible mostly to the Bremsstrahlung continuum, and this is what we measure. And so this is one first thing about that I will start mentioning high resolution spectroscopy, that we could do this that we cannot do today with CCDs, that we could measure the line broadening for different elements, for example, oxygen, sulfur, iron, etc., and understand in better detail this prompt heating mechanism. And so you will hear me mention that several times. Of course, in order to do that, you need a high spatial resolution, because if you have a large spatial resolution, you will integrate across the box, and then you have to take into account the cooling heating. You start to mix the ejecta that are inside with the shocked ISM here that you don't want. And so for all of those questions, you want high spectral resolution and high spatial resolution at the same time. So you see me coming with XIFU, that all of this, of course, is related to what I will mention later on. So now back to the ejectas. As I mentioned, there are some, so we can in numerical simulation, we can do the kind of games that is shown here on the left-hand part of the plot here. We have some modeling of the core collapse supernova, and we can follow them very early from the first milliseconds to seconds and days after the explosion, but we don't have any observation to be compared directly with those numerical simulation. Of course, you can generate light curves, etc., but you don't have a map of the ejecta at one day. And we will not be able to obtain that even if it was a galactic supernova, it's too small to be resolved. So what we can do is wait a couple of centuries, and then we look at the supernova remnant. And here, this is the very famous CASE images in X-rays. And the different colors, the yellow, the green, the purple, are ejectas from silicon, sulfur, oxygen, and iron. And you can see that they are not homogeneous distributed. And so there are some inhomogeneities that are here. And mostly we think now that they are related, that they were not acquired during the evolution of the remnant, but that they reflect the inner early on anisotropy of the explosion. So the question is, what can the remnant tell us about the supernova, and what we can study to have an idea of what was the explosion mechanism? And the key observable for that are manifold. So the ejecta distribution velocity. So first the map, that is the spatial distribution, then the velocity distribution, then look at the abundances. What is the speed of those ejecta, etc. So the same, the first slide was general. Here, I'm going to first focus on type 1a. As you know, type 1as are cosmological candles, and we use them for a long time for cosmological purposes, but we don't know exactly how they explode. And there are several scenarios, and it's funny that it has been accepted as a candle, but we don't know how the candle burns. And so there are different scenarios. One is called the single degenerate, and degenerate means a white dwarf that you have at the center, and you have accretion from a companion, and then you reach a critical mass, the Chandrasekhar mass, and you have some ignition that will happen starting from the dense core, and that will produce some elements, in particular manganese, chromium, and titanium. And in this case, in the type 1a also, you can look at optical and see whether the companion star is still there. And if it has some peculiar velocity, because you have the binary system, then one escapes. And you can have a look at this. In the double degenerate scenario, the idea is that you have two white dwarfs orbiting each other before the explosion, so you don't see them that much in X-rays. After the explosion, you don't have a companion, you have nothing left. We should expect some gravitational wave from that kind of inspiraling system. And here the idea is that at some point they will spiral and one will be tidally disrupted or they will collide. And this is a lower mass white dwarf thermonuclear supernova. And so the key diagnostic between those two is those rare elements abundances and then the spatial distribution also of those ejecta. And by preparing this talk, I found this really nicely drawn press release from Kavli IPMU in Japan, where they explain that. And so the idea is that you have here, one of the key things is that in the single degenerate scenario, you have accretion of matter at the exterior of the white dwarf. And so you accrete, and the pressure inside will increase. And the ignition starts from the core. And so you can imagine that the ignition from the core doesn't have the same thermodynamical properties that in the second case, where they will inspiral and then one will be tidally deformed, and the ignition will start with 1, 2, 10, we don't know, ignition point from the surface, and then it's a deflagration that will go around the surface. And so the temperature, pressure, etc. parameters will be different, which will lead to different abundances, and in particular, high abundances of manganese is expected in the first case, and lower manganese. Iron is always, but really the ratio of iron, nickel, and manganese is really a key to disentangle. And this is what has been done in the past. For example, here you see one spectra of this peculiarly shaped supernova remnant 3C397. So the rectangle that you see here in the bottom column is not an artifact from the CCD, the field of view, or whatever. It is a rectangular remnant, probably due to some interaction with the CSM, but that is really strange. And it is not only strange in the morphology, also the spectra that you see here of Suzaku has very strong nickel-manganese lines. And so Hiroya Yamaguchi and colleagues have looked at the ratio of abundances and compared them to different type 1a explosion models, where you can vary, for example, whether it is a near Chandrasekhar mass in blue or sub Chandrasekhar mass in red here. And for example, doing the same thing with Tycho, Kepler, and this one. And you can see that Tycho and Kepler live rather in the same space of nickel-manganese iron ratio. But this one, 3C, is really different and could be probably coming from a near Chandrasekhar mass explosion. So, of course, with Suzaku, we have this, and then some simulation were performed of what we could see with Athena XIFU. And of course, if you compare the CCD resolution of XMMPN that is shown here with XIFU, we'll be able to resolve the nickel lines and the abundances down to a much smaller range, so that we can constrain really the parameters, for example, of the density, the mass of the white dwarf companion, etc., with much better details. So continuing on type 1a supernova remnant, so I mentioned about Tychos, and I mentioned also that we can study how the ejecta are distributed and the asymmetries to try to understand if the explosion was asymmetric or if it was rather spherical, coming from one point, ignition point, or another. And so this is some work from Leila Godino, a PhD at CEA Saclay. And so the idea is that we use the Chandra data cube. So Also, you will be hearing me a lot talking about, let's look at data as a data cube as 3D. And when I say 3D, I mean raw, deck, and energy is the third axis. And so we have developed and adapted some method. One of them is a component separation method. So you start with a cube and you want to decompose that cube into main components. It is not exactly like a PCA, but principal component analysis. In the general spirit, it is the same idea. And it is blind in the sense that you look at components that are that differ in morphology and in spectral behavior. And so when you start with the data cube here, this is what the method that is called generalized morphological component analysis outputs. And so we focused just around the silicon energy band. And the method was able to retrieve 3 components, 2 Gaussian-like components that are in fact the silicon line that are redshifted and blue shifted, and a continuum line that is the synchrotron component at 1.8 keV. And those are the images on the bottom panel that are associated with those spectra. And so you can recognize on the left, if you have looked at some synchrotron images of supernova before, the filamentary shape that is typical of the synchrotron, and then the fluffy components, component 2 and component 3, that are those silicon emission clumps. So those clumpy features, as I said previously, are mostly due to the relative instability that are created those fingers, and then everything is collapsed into the same plane, and so you get those profiles. And so what we did here is to take component 2 and component 3, the image of the red, dominantly red shifted and blue shifted, to have an estimation of the redshift, the average redshift along the line of sight for every pixel. And this is the image that you see here on the left plot. And so it is a way in which we can characterize the redshift not in big regions where you do a spectral fit, but down to arc seconds level. And we have this incredible map where you can compare and look at the redshift, the velocity redshift down to very small details. All the symbols that you see are a comparison with previous work that we're using, for example, RGS or ACIS to measure the redshift. And in all of the cases, they agree when the color, when there is a blue circle, it means that they found a result that was blue shifted, and it perfectly matches our results here. And what is particular is that you see that so the redshift is clumpy. This is due to the velocity is also, there is a clumpy field. And then what we notice is that it's more blue shifted on the north and more red shifted on the south, meaning that you will have some elongated explosion along the line of sight. And what's interesting is that Tycho looks very spherical if you look at the Radek, but then what we couldn't know, and that is revealed here, is that it seems that it's not symmetric along the line of sight. And so what could this be? Is this some, due to asymmetric explosion? Is there some relation with the ignition model of the thermonuclear explosion? And so we investigated also that to have, the idea was to have really a 3D ejecta dynamics, X, Y, and Z. And so for the X and Y, we don't use the Doppler effect, but we use the proper motion, because there are several observations, several years across. And so you can look at one blob and the same blob 5 years after, and you can draw all those vectors here, inspired from optical flow methods. And you can have this incredible field. Usually when we measure proper motion in supernova remnants, we have 10, 20, 30, 50 vectors to have an idea. And here we have 1,500 vectors to really see down to really small details how the ejecta evolve across the map. And interestingly, you can see the blue vector are the fastest one, 7,000 kilometers per second. So those are ejecta nodes that come at very high velocity. And then you have some, on the northern region, you have some vectors that are slowing down, probably due to interaction with the CSM. So it's really rich data set in which you can explore both the ejecta and at the same time how the ejecta and the remnant interacts with the surrounding. And so one of the questions that was left over from the first study is what's this north-south asymmetry due to? And so we wanted to look at whether this north-south asymmetry could be visible if you look at the temperature map, for example. If you look at the ejecta temperature map, is there some kind of similar behavior that is seen? And so we did this spatially resolved spectroscopy analysis on over 200 regions that you can see in the bottom panel. And one region, the spectrum looks like the one shown above. Tycho here has been observed for 700 or 900 kiloseconds with Chandra. So those are very deep exposure. And you can see that there is very little noise on the spectra from those observations. And so here, what you see is the abundances, mapping the abundances, the ratio of abundances to silicon in all those regions. And there is no very clear, and so here, this is abundances, we also have temperature. And in the temperature map, there are not really clear dipolar emission maps that is leading us to say that this asymmetry here seems to be due to the inner explosion and not be due to some interaction with the interstellar medium. And so also what is interesting is that if you take those maps, you can see here that there seems to be higher ejecta, higher abundances with respect to silicon, at least magnesium, for example, and also calcium in the lower left part of the remnant. This is also where we were seeing in the previous plot that you have those ejecta not going out. So this could be due to an initial explosion. And by taking those 200 regions and looking at the abundances ratio, what you can do also is to compare that with nucleosynthesis model. But instead of having one point, usually you say, I take one knot that I hope is representative of the SNR, and I compare it with nucleosynthesis. Here, for each element, we have a histogram of the different condition of distribution across the remnant that is compared here with different nucleosynthesis models. And it's none of them is a perfect match to our distribution, but at least the green curve, what is called the violent merger method, doesn't seem to reproduce well, in particular, the magnesium to silicon ratio. And the one that is closer to our distribution seems to be the DDT, that is the delayed detonation transition model for type 1a. So what about core collapse? So core collapse is a different scenario, but you have this very high energy deposition of neutrinos. When we talk about 10 to the 51 in kinetic energy, remember that this is 1%. The kinetic energy is 1% of the total energy budget. Most of the energy goes into supernova, into neutrinos in the supernova. And so that's 10 to the 53 erg that we have here. And again, from numerical works, people have shown that if everything is spherical, it doesn't work. And so you really need those instabilities in order to revive the stalled shock. And so there are different kind of asymmetries. One is this sloshing motion SASI that is creating that inspiraling asymmetries that is mostly creating large-scale structures. And then you have this neutrino buoyant convection where you have the neutrinos shining in the center, heating the gas, and then it's making like when you're boiling water, those boiling bubbles that are here. And so those leave impact also in the remnant. And for example, what we have done also is to look at those ejecta symmetry in Cassiopeia, that is a core collapse. And so using the same methodology, we're able to do red shifted, blue shifted for all the elements that were in Cassiopeia. And for example, what is shown on the right panel here is the centroid position of each element, red and blue. And you can see that, for example, in the iron, most of the red shifted iron is the top right part of the ejecta, and the blue shifted is on the other one. So again, it's creating like this bipolar structure. And what is interesting is that we found out that most of the emission, most of the mass seems to be red shifted, so going away from us, and it's going at the opposite direction of the neutron star. And this is something that can be compared also to numerical simulation, in which you have the drag, how is the neutron star, the initial kick of the neutron star. This is related to the explosion mechanism. And going back to this neutrino, something that I find really interesting is that by looking at Casey, for example, if you look at those rare earth elements, titanium and chromium, there is a little bit of an excess in those regions here, the ones that are the same one of the iron, and those have high entropy due to those buoyant bubbles of neutrinos. So high entropy means that they are low density, high temperature, and that those bubbles are pushing the ejecta outwards because they were very close to the neutrino source. And so with those titanium chromium ratio, then you can do something that is interesting. You can compare that to the neutrino-driven convection explosion. So again, by looking at the ratio of titanium, iron, chromium, iron, etc., you have some models in which you can change the peak temperature of those neutrinos and the entropy, etc., and see what match better. And so this can constrain the core temperature, the temperature of the core of the explosion, and how much the matter has been exposed to neutrino heating. And so in this example, they say that this is an evidence without neutrinos in the engine, you cannot explain the ratio that is observed here. And so this was done with Chandra, again, a simulation here of Chandra and then XRISMs. And so here it is shown that, of course, with XRISM, chromium, manganese, etc., will be constrained down to much better accuracy to compare with those models. And more recently, again, the manganese was also one of the key things to be compared here. And so the manganese is really a very small deviation around 6 keV here. But what is interesting in that very recent article is that they said that you can constrain very detailed parameters of, for example, the neutrino interaction, meaning the luminosity and the temperature of the neutrinos inside the explosion related to the amount of manganese that you can detect. So when you think about it, it's a bit crazy that measuring manganese can tell you about the temperature of the neutrinos during the explosion. That's an indirect model-dependent measurement, but still, I mean, it's quite amazing it's very hard to detect a neutrino, but here we say that we can measure its temperature. So moving forward, of course, we have this generation XRISM, Athena, and also the concepts from the US colleague that are LEM links from the NASA side about micro-calorimeter. So I don't need to convince you that micro-calorimeters are awesome and that this is what we see, for example, for typical simulation from XMM, and this is what we expect to see with XIFU. I will show exactly in the next few slides that we will probably never see something as detailed as that, not because of the noise or the quality of the CCDs, but just that for extended source intrinsically, along the line of sight, you have different redshift condition, etc. So this will be mixed by the different plasma that are in the line of sight. So as you know, Athena has restarted the industrial phase. And so we are out of the troubles that we were a year and a half ago. So we have good prospects for the future. And so one of the simulations that I did for that ESA SPC back then was have an idea of what Athena XIFU can say about chromium and manganese line, for example, in Casey. And so the results that were shown before were combining observation from Chandra up to 1.5 megaseconds of observation to detect that manganese line. And here we show that with a little bit more than 50, 60 kiloseconds, we should be able to detect whether we have 3 EV resolution or 4 EV resolution. That doesn't matter that much. We should be able to detect manganese and chromium line. Let's say 100 kiloseconds versus 1.5 megasecond with Chandra. However, reality will be slightly more complex if you take that line of sight velocity. And so that's why it's important to look at something that is out in the plane with less confusion, and hence the need for a good spatial resolution. So without waiting for the future, we already have some great first example of data that have been shown by XRISM. And so here we'll show the the one that you have already seen, but I wanted to put it in perspective with what he told me. So the observation was shorter. There was also a gate, a valve a filter that was closed. But this is what he told me. So in 5-6 years ago now. And so if you look at the iron line, it was basically 5, 10, something, 20 photons. And look at the spectrum that we have now. This is quite incredible in the iron line. And despite the gate valve being closed, you still see the silicon line is so bright in that object that you still see the silicon 1.8 keV line. And the sulfur line is incredible. You see a doublet in the sulfur line. This is for, I think, 150 kiloseconds of exposure, but this is really exquisite data. And also what surprised me is that if you look at the extend image, I was expecting the PSF. They announced 1.3 HPD, half power diameter PSF, but what I realized is that the center of the PSF is very peaked with large wing, which is creating this 1.3 arc minute. But I looked at the XMM observation of that remnant, and XMM looks better, but not so much better. So I was expecting that the PSF will be much worse than that. And so it's really non-Gaussian PSF. So that's good news that the spatial information, at least from the images, will not be as blobby as I expected. But still, the PSF it is what it is, and this will be a challenge for the analysis of extended sources. And this is, for example, very nicely put by François Mernier at the XRISM workshop back 2 months ago. And so, for example, here is a nice illustration of the green grid is the field of view of XRISM, and then you have the PSF here. So basically, the PSF is not self-contained within the field of view. And you will have a high crosstalk that is shown here. Every pixel will have a crosstalk with the other one. And result will be that one. And so you have a low spatial resolution, big pixels, and a high crosstalk. So this is what he called spatial spectral mixing. And then this will be quite problematic. If you want to analyze the spectrum from 1 pixel or from 4 pixels, you really need to take into account the crosstalk from the neighbors. And so this is where really I want to emphasize that a good imaging capability gives you a good spectral resolution. And this doesn't seem obvious from the beginning, but here, this is one of the movies that we produced with Christian Kirsch using 6D to show. So we took a numerical simulation from Casey and processed it through 6D to simulate a 10 kilosecond exposure of Resolve and XIFU. And the spectrum on the right panel is extracted from that box that is the resolution element that is related to your PSF. And so it's amazing with XIFU how much details you can see. You can see the different rings of the ejecta. This is the redshift effect. In the first part of the movie, we see the red shifted part of the silicon lines, then the blue shifted part of the silicon lines. And basically with Resolve, it's harder to see those details. But most importantly, if you look at the silicon line, we see 4 different peaks with XIFU. We don't see them with Resolve, and it's not because XIFU is 2.5 EV and the other one is 5. Those peaks here are much broader than the 2.5 EV resolution. Here, the difference in spectra is entirely due to the pixel size and the PSF. And so what I want to emphasize is that for extended sources, there is a direct correlation between spatial and spectral resolution. If you want 1 EV resolution, you cannot do it with a larger PCL because in extended source, you will have a crosstalk between the pixels. And also, not only in the pixel, but also along the field of view, along the line of sight, of course, you will have that crosstalk as well. So here is an example of that simulation, a 3D simulation, and you produce an XIFU spectrum for each cell along the line of sight. And so what we observe is the black one, but in fact, this black curve is composed of a collection of red, blue, red, blue, red, blue that have different redshift, but also different temperatures. And so This one is harder to disentangle. Even if you have good PSF, you still have to live with this. But what you can do is go to the border of the remnant, and if the PSF is good enough, you will not be contaminated from the inside in order to have a spectrum. Because imagine that if you want to measure ion line broadening, as I said at the beginning, well, here you will not be dominated by the broadening of the KTP, but of course of the line of sight contamination. So in the last part of the talk, if I have still 5 minutes, is to discuss about the challenges that this will bring about the analysis tool. And for example, why do we have spectral imager in the first place? Why do we want them? So one of the things that we do is that we want to map the properties of the plasmas. For example, we want to map the temperature in Perseus. We want to map the abundances. But so far, we have those 3D data sets, those IFU, but we treat most of the time each pixel independent from the other one. But the data set that we have is really a 3D data set. And we have not been using that to the full advantage. And this is some work by Julia Lascar here to make an hyperspectral fitting package. That the idea is that you will fit all those pixels at the same time and using the information from the neighbor. So this is a decomposition here in which each pixel has a different parameter, and then you have that amplitude map. And what you want to minimize is, so we use a machine learning generative model to have the gradient of our model. And then we add a spatial regularization, meaning that we don't want each pixel to vary completely and to minimize outliers. And so as we know also the gradient of the model, we can do a gradient descent on the entire cube, not pixel by pixel, using modern tools like JAX to have a fast gradient descent on everything at once. And so here is the paper that has been accepted last week in ANA for benchmark. So we do the same numerical simulation of Casey that is shown here with the simulation kindly provided by Salvatore Orlando. This is the ground truth. So this is from one side only. And this is what was reconstructed. The redshift was reconstructed for every pixel with sushi. And then with the classical method, when I say classical, is really one pixel, an X-spec fit, pixel by pixel. And so, of course, this is very noisy because those are the example from that specific pixel. And so the data that you see here in blue are rather noisy. There are not a lot of counts. And in that very specific pixel, Sushi was able to recover the temperature very accurately, and also the redshift. Look at the redshift that we simulated and the redshift that we recovered. Although there was little information in the spectrum, but this spectrum is using information from the neighbors as well to be able to fit the spectra. And in the classical fit, if you see here, if you compare the dashed line and the solid line, this is the simulated one, and the recover one, it was not able to do a good job. And the redshift and every parameter were not recovered. And so on the real data, this works also on the real data. That's a good thing. And so this is again Casey, where we focus on the iron line, and we were able here to fit the properties of the iron line down to 2 arcsecond level to measure the temperature of the iron K and also the redshift down to very small regions. So and the last thing I want to say is about, so we have those objects and we have those models, and we're trying to minimize a model. And there is always this question of whether we have a local or global minima. And so this is nicely illustrated here in this, depending on where you will start, you will not fall in the same region. And so this is 1D here, but when you have 10, 20 degrees of parameter, imagine the landscape like this, and it can be quite complicated. So I've recently digged a lot into this nested sampling algorithm. And so I don't have time to go into the details, and you can look at those very nice review, and in particular also that website here that has a very nice tutorial for that Bayesian X-ray analysis package, BXA. And I encourage you to look at this, and UltraNest, the package that has been used in this one. And the idea is that if you look at that likelihood that is shown here, if you use X-spec, it's impossible. You will stop, and then you will not be able to see the 2 minima that are shown here. And the idea of nested sampling is that you will draw random points And then all the technicity is in doing the likelihood restricting prior sampling. So you want to draw points only in the region that have a better likelihood than the one that you removed before. And so you will quickly can have an estimation of what your likelihood landscape looks like. And you can see that you can have the two solutions at once, the posterior distribution for the two solutions at once. And so I wanted to test that and compare what XSpec does with nested sampling. So I used the nested sampling here to draw all those VREDIS color points in the background, yellow and green. And so this is giving you the full likelihood landscape of your minimization problem. So the color is the likelihood. And so green is blue is better and yellow is worse likelihood. And the black and red are XSpec descent starting from different points. And you can see that starting from different points for different parameters here, you don't end up in the same location. This is what was shown before, but here it's a very nice way to show it. And you can see also the white contours are the 3 sigma contours from the posterior distribution. And you can see that in none of the case, XSpec was always inside, it was always outside of the 3 sigma contours. And so in some complex cases, it's also even more problematic. If you look at the ionization timescale tau versus redshift on the right-hand plot, you can see that there are some complex degeneracies and that XSpec will never be able to really explain and visualize and enter that highly complex parameter space. And so this is what is shown here. This is the likelihood space of an XSpec fit in red and in black, and the points are from the nested sampling. And so you have to imagine that you have to travel inside that high dimensional space. And at some point, XSpec was able to enter into the valley, into the tube, and go down inside the tube. But the black one was able, and the red one did not converge. It entered and it stopped before. So this is just an illustration of how complex the likelihood space are. And because you have high resolution data and high statistic data, the valley is very small. So it's hard to get into because the valley is very small. And so all of that to say that with the great data that we have in the archive with 1 megaseconds and the great data that we will have with XRISM and Athena, we need a new generation of X-ray tool to face those challenges. This was part of the AHEAD 2020 European program that, and I list here some of the works that have been carried out in that direction. And also, for example, for Athena, there was Didier Barret and Simon de Pourquet that recently published a work to do fast inference for the parameters and the posterior distribution. And so this leads me to the conclusions is that, so going back to the science, supernova remnants are excellent physics laboratory that can probe lots of different physics from shocks, collisionless shock physics, acceleration, nucleosynthesis, etc. And X-rays is one of the key wavelengths to do that because you can track the non-thermal distribution for the acceleration things and also the thermal distribution where you can learn a lot about nucleosynthesis again, etc. And with existing observation, we start to pinpoint the explosion mechanisms for a few remnants, the very white ones, and we have detailed nucleosynthesis mapping. Again, this thing of measuring the neutrino temperature, I think that's quite amazing. And we still have a gold mine in the existing archive. Some of them have megaseconds of observation, so it's still lots of science to do. And right now we have seen the incredible first result from Resolve. But in order to do spatially Resolve, if you want to analyze pixel by pixel the spectrum, there is this spectral spatial mixing effect that needs some thinking of how to handle this. And what I want again to say is that for the extended sources, and this is why we fight for Athena to keep its high PSF and small pixels, that a good PSF makes a strong difference spectrally, so that you need high PSF. You cannot have 2 EV and a 30 seconds PSF, because in the end you will never reach that effective 2 EV resolution. So you cannot say it's okay, we do that, and maybe for some sources it's okay, but not for the extended sources. And Athena, in my point of view, is all about, not only all about, but about extended sources, because this is one of the key difference between XRISM and Athena will be the PSF and the spatial and the IFU. So of course there are many other differences for other topics, but at least for supernova remnant, this will be the key difference. And there are many analysis challenges ahead, and I think we need to reinvent some of the way of we handle the data. And XIFU is an IFU, so we need to think of it in the 3D term and not separate images from one side and spectra from the other side. And already the data from result are a great data set to explore those new techniques. And we need also, from a more larger point of view, to keep this fostering our vibrant European X-ray community in the distance between now and Athena. And the methodology is one thing, but there are, of course, many other pathways to do that. And that's it. And I will leave you with that other simulation that why we take questions of Athena for Kepler, where you can see from the side, again, it's a cube, and you can see from the side all the lines. And the intensity here is color-coded by white, means more intense. Thank you.
Thank you very much. Very, very nice. I just an applause I will do for everybody. Thank you very much. Very nice simulation, actually, this. So let me ask if there are any questions. If you just raise your hand, I will let you speak. Whoever has questions. I don't see hands. No, in the meantime, maybe I can ask you. I have a few. So in the meantime, while people are thinking about this, so I have some questions which actually we were asked in the SRDT several times when we were sort of studying the supernova remnant topics and what Athena will bring and all the things that you know very well. You did several very nice videos for that. So we know how many are the X-ray bright supernova remnants in the galaxy. And there are not many. Maybe with, let's say, in Athena and XMM, with 2 hands, it's enough. With Athena, of course, sorry, in XMM and Chandra, with Athena, we can go deeper. So same kind of study can be done for more sources, of course. So a question is, to your view, for how many of them we can really, with Athena in the future, have detailed 3D and nucleosynthesis maps, and how this addition will actually bring new information on this kind of physics with respect to the field that we could study now?
Yeah, so for now, I think that mostly, of course, Casei is the brightest one, is the one that has been, and this neutrino thing, for example, has been mostly done only on one, so Casei. And as you said, in total in the galaxy, it's about maybe a dozen supernova remnant that we could go deep, that are bright enough to go deep, not too small, etc. And so far, mostly we had one core collapse and one type NA, so Tycho, Kepler, so 1 or 2. But so it's really going from 1 to 5 each, or 4 or 5 each. So it's multiplying the sample by a factor of 5 or 6. And I think that we haven't done the numbers, but in the LMC with Athena, we probably could go. So maybe N132D is not too small, so that you can really resolve them. And then N103B also in the LMC is not too small. So there are a couple of extra in the LMC, and it will be interesting to see, for example, if the manganese, if all those parameters are similar in the LMC, where the metallicity of the host galaxy is different, how these plays with the explosion mechanism for type 1s, etc.
Okay, thanks. Very nice. Any other question? Yes, I have Maria and Massimo. First, Maria, go ahead. I think you can speak.
Yeah, can you hear me?
Yes.
Yes.
I'm on the train, so probably you can hear me. So I want to ask, what is the Special resolution. And because actually the question is what are the opportunities to study extragalactic remnants? But like extragalactic, I don't mean with LMC, SMC, but of more distant galaxies. For example, about 5 megaparsec.
So you have some echo, so it's hard. I think so.
Sorry?
Yeah, now it's better. Can you repeat?
Yeah, I actually asked what is the special resolution, and I'm asking this because I'd like to know what are the opportunities to study extragalactic supernova remnants, but further than LMC and SMC.
Okay, so the spatial resolution of XIFU of Athena is not yet fully defined. So the goal is to have better than 8 arc seconds, I think, the last numbers. So in the end, it will be better than XMM and not as good as Chandra. So it's somewhere between those two. And so it will be hard to do something beyond LMC and SMC. I think LMC and SMC, in order to spatially resolve, I mean, of course, then to observe supernova in external galaxies, young supernova that exploded a month ago, a year ago, this will probably be possible in nearby galaxies. But then having a map of the ejecta where you can make the difference between left and right, this will be limited to LMC and SMC.
Yeah. Okay, just the detection, I think, would be fine. Thank you very much.
Thanks. Massimo, go ahead.
Okay. Can you hear me?
Yes.
Okay. So first of all, thank you very much for the very nice review, and which is projecting us in 10 years from now, or what will be the power of the micro-calorimeters, and that was really great. I have actually one comment and one question. The comment is, okay, you make a clear case for the PSF importance when combined to energy resolution. But I think also you didn't mention the effective area, because at some point you want to fill in not only your energy beams, but also then your special beams, I mean your pixels. And for this, I mean, to fill in both simultaneously, you need really, the key is also the effective area. Okay? And this has been the real actually challenge for all optic developments, and is nowadays the big challenge for I think the X-ray optics developments. And really Athena is outstanding in this combination of these three parameters altogether. So this was my comment. Then my question is more related on the synergies. So you mentioned synergies with other wavelengths, even with neutrinos, and which is great. I was wondering if you could expand a little bit more about the synergies you see, say in 10 years from now, with future PV/PEV of great observatories, which are being built. And if you see where in your opinion could be the synergies, or you think there are still at the end different astrophysics that they'll address. For example, will you from X-rays be able to touch on the PEV generators sources? Will you be able to say something from X-rays or vice versa? I mean, can you address a little bit where you think it will be the observations?
Yeah. So the second one is a tough one. The first one is a good comment that indeed you need high effective area. And I found it interesting, if you look at the movie that is shown here, is that XRISM and Athena in the spectrum that I extracted here, they have more or less the same number of counts per beam here, just that if Athena has smaller pixels, then you need a higher effective area to fill those beams. And this is why in the end, in the extraction region that is bigger, You need this higher effective area in order XIFU to really compensate for the smaller beams. So yeah, completely agree. And for the second comment, so maybe you have in mind the CTA or gamma ray astronomy versus X-ray astronomy. And yeah, I think so for the nucleosynthesis and the ejecta, not much. Of course, those are two different topics. But of course, where there is clearly something that can be done is for the particle acceleration. And something I think that could be interesting. There are several possibilities with a high collecting area. For example, people have been looking for the secondary synchrotron from hadronic emission. So if you have hadronic emission, you have secondary electrons that should make some synchrotron. And so that should have different properties from the first primary electrons. So maybe this is something that high effective area emission, not XIFU specific, but could find. And also, as you know, for the hadronic emission scenario, you need to be able to constrain the densities and to have a map of the densities of the thermal emission very well. And this is something that XIFU could be able to do, to have really a good mapping of the thermal emission, especially, as you know, for example, there are some supernova remnants, like the famous RxJ 1713, that the X-ray emission is dominated by synchrotron, and we have no trace of the shocked ISM. We have some trace of the ejecta, but not of the shocked ISM. And so with XIFU, you could identify and measure the density, which is one of the key parameters to model the energetic budget that goes into the protons in the acceleration, and therefore also to have an idea of the PeV energies, etc. So yeah, I think definitely XIFU and WFI have some good synergy with CTA for the particle acceleration.
Thank you. Thank you very much.
Thank you very much. Further questions? No? If not, we're already 5 minutes late. Okay. If not, let me thank again Fabio. It was a fantastic talk. Thank you very much.
Thank you for the invitation.
And see, we will have the next webinars in a couple of months, early May. So have a nice Easter holidays for those in Europe and the US. And see you very soon. Thanks, Fabio, again.
Bye-bye.
Bye.